Assalamualaikum warahmatullahi wabarakatuh. We are from Group 4. Our group name is Faraday Flux. Okay, today we are going to present about power system protection project, which title Impact of Instrument Transformer on Protection Scheme Sensitivity. So this is our group member. First, me as Fidaus. We have Izzat, Razak, Daniel and Ahmad. For the visual presentation, we divide into the several parts. As an example, I present about the introduction and conclusion, while Ikram Daniel present about literature review, Ahmad present about simulation, Razak present about the result and discussion, and lastly, Izzat present about the methodology. Okay, we go to the next part, which is introduction. Protection scheme in electrical power system are crucial for detecting faults, disturbance, and irregularities. Instrument transformer divide into two, which is current transformers and voltage transformers. These two transformers improve sensitivity by measuring high primary value and providing accurate representation for protective relay. The meaning of Faraday flux is a magnetic field created by primary current and secondary currents. And Faraday flux also can affect the sensitivity of protection measure. To reduce the Faraday flux effect, transformers design, material, and maintenance must be carefully considered. That's all for my part. We go to the Akam Daniel, which is literature review. Thank you.
Hi, so I will continue this presentation for literature review. So first of all, the first part of literature review will represent the types of instrument transformer, where there are two main points for instrument transformer, which is current transformer, the CT, or the voltage transformer, also we know as VT. So the CT measure high current in power system and scale them down for measurement and protection equipment using the primary winding and a secondary winding. For voltage transformer, it measure the high voltage and step down to safe level using primary winding and secondary winding, either electromagnetic or capacitor based. For the next section of literature review, it will represent the source of error and uncertainties, where I provide two main points for error and uncertainties. The first one is magnetic saturation and not non-linear behavior. The second one is burden and impedance effect. So for the first point, instrument transformer may experience the magnetic saturation, causing distortion in output waveform and inaccuracies in measurement due to non-linear behavior. The second point, instrument transformer burden impedance affect measurement accuracy. Furthermore, the deviation from specific range cause error. Okay, the last part for literature review, also I provide two main points for different protection scheme, where the first one is differential protection. What is differential protection? It's a scheme of protection transformer, generator, motor using current transformer to measure current. Meanwhile, the error can affect the balance and cause incorrect calculation. The second point of different protection scheme is line and busbar protection, where the transmission line as busbar protection rely on accurate instrument transformer measurement. Meanwhile, the error, we know it can affect the sensitivity and false tripping. So that's all from literature review. I will pass the methodology section to our group member. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Izzat Imran bin Nordin. For my part is methodology. This is a flowchart. Show the flowchart below showing the flow of operation of simulation performance to make a project successful by using the design software. This is start. Create a test system model of power system using MATLAB Simulink. After that, design a basic protection scheme using an instrument transformer. After that, is choose the parameter of each block used. After that, run the simulation program. After we run a simulation program, we have include a fault. We have when we have a fault, yes, is collect the data and modify the simulation. And the fault is no. We need to have collect data and analyze the data for the lastly is end. After that is the block diagram. The block diagram show the impact of instrument transformer on the protection schematic sensitivity. High voltage current source provide scale down signal requiring accuracy and calibration. The Burnett and saturation effect of the transformer affect the scheme response times. Protection relay analyze the signal, effective sensitivity and fault detection. Accurate fault detection, improve system reliability and reduce human damage risk. This is a block diagram. High voltage source current. After that, instrument transformer have a CT and VT or PT. After that, accuracy and calibration. After that, Burnett and saturation effect. After that is scale down signal. After that is protection relay. After that is fault detection and decision. Lastly is system response. This is a circuit or structure of simulation. First structure is power system structure. Second structure is protection schematic structure. For the last is a current transformer CC structure. The instrument transformer have a two is CT and PT, but my group choose a current transformer CT structure for the simulation. Okay, thank you for me.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Ifram Rosli and my metric number is DE200F4. So today I want to present the simulation about our protection system. So from this circuit I want to tell one by one. So as you can see, they have two part, the first transformer and the second transformer. For the first transformer is for the step down, step up. It will step up from 11 kilovolt to 33 kilovolt. So for here, for the second one is the step down, which is the 33 kilovolt to the 11 kilovolt. So we set our power going into the discrete, and our time to simulation is 0.25 second. So first I want to show the stair generator. So from here we can change the amplitude here to give fault or not. So for the first one is the 000, which means didn't have any fault. After that I click run and just wait a little bit. After we run it, it can give us the graph. So we click the scope before, and it can be like this. So this is the before the transformer, and then we just click the after. So the after, if did not have any fault, so the graph before and after is actually same, also for the voltage and the current. Next I will change the amplitude at the stair generator. I will change here into 1. So if I change 1, it tells that it has fault at the 0.02 second. So we can apply and OK, and then I just run it again. So just please wait a while, and from here we can see the change at the after the transformer. The before is normal, but at the after have some fluctuation. So I can show here for the voltage. Okay, you see here it's same. So the straight one, which mean we have fault in the circuit, and then it became normal again. So for the after voltage, we can see that you have a fluctuation after the fault. So with for the first wave, it's normal. Then after the fault, we have the fluctuation at our protection. So from there we can conclude that if we put fault at the transformer, the voltage and the current for the transformer, we have a fluctuation. So this is for the voltage, and this one is for the current, also have the fluctuation. So this is for the step up. So the step down also same. If I change the amplitude at the step down, so the graph for the voltage and the current also have the fluctuation. So that's all for my part, and my friend will tell more about the result from the circuit. So I continue my part about our video simulation for the CT, which is the current transformer saturation. So at the source, we set it to the 50 Hz and use 120 kilovolt RMS, and then from the source it will go through the transformer here, which is the transformer is to measure the flux and the magnetization current, IMAC. Then it will give us the graph. So here the graph for the CT. For the top one is for the IP rim, which is as you can see here is totally same from the beginning until the end. But for the CT flux, the graph will be decreased, not decrease, but will become more lower from the beginning. Like here is from 1 until in the end it will give below 0.8. So this is our CT, our current transformer for our system protection. So that's all for the current transformer. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Razak bin Ahmad Syukur, and I will be explaining on the result and discussion for this group project. So firstly is the power system structure. So this is our power system structure where the two transformer is equipped with a protection shim. So the 3-phase fault here is added in order for us to add a fault in the system. So firstly is the current before the current and voltage before the transformer, and current and voltage after the transformer. So it is as expected, where the output current and voltage is identical to the current and voltage before the transformer, where there is no fault that occur in any of the system. So adding fault in the system. So this is the fault that has been added at the time of 0.02 second. So it can be seen for the current and voltage before the transformer, where it will stop working for the system for the time of the period where the fault occurs. For the current and voltage after the transformer, it is the same, except when the system try to recover from the fault, there will be a voltage or frequency fluctuation due to inrush current. So here we can see the fluctuation that happened in the system for the system to recover after the fault. So in order to counteract the problem, we increase the winding parameter. This can be seen for the R1, L1, R2 and L2, which is from 0.002 and 0.003 to 0.006 and 0.007. So it can be seen for the current and voltage output from the graph, it is getting better in order for the system to go back to the steady state where there is less distortion or fluctuation that happen due to inrush current. So basically the fault that happened in the system is a three-phase fault to the ground, which cause transient stability issues leading to voltage and frequency fluctuation. So this fluctuation can disrupt the operation of the power system and may result in cascading failure. So after increasing the number of turns for the winding, the fluctuation of the system after recovering from fault is better than the initial winding. This is because higher winding impedance help to limit the flow of short duration current transient, such as the inrush current or fault current. So in total, it will have a better control of current fluctuation, thus enhancing the stability of the system. So a higher turn ratio led to a higher sensitivity, enabling the detection of lower fault current, thus achieving the selectivity by allowing for discrimination between fault current and ensuring the operation of only the relevant system. So the protection shim structure, so where it used a 3SR flip-flop. So the first one, to see the difference, here is a circuit without the protection shim, and this is with the protection shim. So it can be clearly seen on the graph output, where for the graph without the protection shim, the system will shut down when reaching the time where the fault happened. And for the output graph with protection shim, it will isolate the faulty section and the system will goes back to the operational system with containing the fluctuation. So it can be observed without the protection shim, the system will completely shut down if any fault occurs in the system. But after installing the protection shim, where it will isolate the faulty section in order to make sure the system stability and reliability to continuously works even if there is a faulty section. So basically a protection shim in this project, where it will isolate the faulty section, so it ensure the system to work even if there is a fault between the time where it will isolate the fault itself. And lastly is the current transformer CT structure. So firstly is the normal operation of the current transformer, where the breaker is set to 1.25 over 50 cycle with no current asymmetry. So the current and voltage are sinusoidal, and the measurement error due to CT resistance and leakage reactance is not significant. So the flux contain a DC component but is still lower than 1 pu saturation value. And next is the CT saturation due to current asymmetry. So the breaker is set to 1 over 50s. So for the first 3 cycle, the flux stay lower than the saturation value. So we can see for the 3 cycle, the flux stay below the 10 pu. So the CT voltage output V2 then follow the primary current. So it is the same for the 3 cycle. And then after 3 cycle, the flux asymmetry produced by the primary current cause CT saturation, thus producing large distortion of the CT secondary voltage. So after 3 cycle, where the saturation, it goes to the saturation value, which is 10 pu, and a distortion of the CT secondary voltage happen. You can see here. So next is the over voltage due to CT secondary winding. So we change the breaker closing time to 1.25 over 50 and the secondary switch opening to 0.1. So this is the switch where we set 0.1. So it can be observed that the large voltage produced when CT secondary is open, the flux having a square wave shape chopped at plus 10 pu and minus 10 pu. So large dphi over dt produced at flux inversion generate high voltage spike of 250 volt. So this is the voltage spike that occurs due to the secondary winding opening, and then this is the square wave of the flux density. So current transformer saturation refers to a condition where the core of a current transformer becomes magnetically saturated due to excessive current flowing through its primary winding. So when a current transformer is saturated, it is no longer able to accurately reproduce the current waveform measurement on the secondary side. So saturation occurs when the magnetic flux density in the core reaches maximum level, causing the core material to lose its ability to further magnetize in response to an increase in current. So in order to mitigate this type of effect of CT saturation, several implementations can be done, such as balanced current distribution or oversizing the current transformer. So the overvoltage can be detrimental to a connected equipment such as relay, protecting device or monitoring system. So that will be all from me. Thank you.
Lastly, for the next part is conclusion. The project examined the impact of instrument transformers on protection strategy in Faraday Flux using MATLAB software. Instrument transformers are crucial for accurately measuring high voltage and current, reducing error and distortion. The study demonstrates the importance of instrument transformer in maintaining sensitivity and enhancing protection scheme sensitivity. The finding from the project can be applied to real-world power system to improve stability, dependability, and safety. I think that's all for our group. Thank you.